Scaling. The next step is to get the prices and the areas on the same scale. The prices are in Toman, the areas are in square Azani, and there is no such thing as a conversion from Toman to square Azani. That would be like a conversion from bushels to Celsius. Pearson, or rather Bravais, used an idea from linear algebra called normalization. Suppose you have a vector, AB, and you want to find a vector pointing in the same direction, but whose length is 1. Any multiple of the vector AB, such as MA, MB, will point in the same direction. Multiplying a vector changes its length, but not its direction. If you divide the vector by its length, the new vector, A over L, B over L, will have a length of 1 and the same direction as the original. This also clears the units. Imagine that the length of the vector is measured in feet. If you divide the vector by its length, then you have feet divided by feet. The result is just a number with no units. It is dimensionless. The same is true when the vector is measured in Toman or square Azani. The length of the vector can easily be found by using the Pythagorean theorem. L equals the square root of a squared plus b squared. This can be extended to any number of dimensions. L equals the square root of a squared plus b squared plus c squared plus. Let's try an example to see if this works. Try the vector 3, 4. The length of this vector is the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16, which equals the square root of 25, which equals 5. The normalized vector is 3 over 5, 4 over 5. Therefore, the square root of brackets 3 over 5 squared plus 4 over 5 squared equals the square root of 9 over 25 plus 16 over 25, which equals the square root of 25 over 25, which equals 1, is the length of the normalized vector. As expected, it worked. P, A, P prime, and A prime are all lists of numbers, so they are vectors. They have lengths just like any vector, and they can be normalized like any vector. In geometry, a vector is normalized by dividing it by its length. The length of any normalized vector is always 1. To normalize P prime, you just square all of the adjusted prices, add those squares and take the square root of the sum. That gives you the length of P prime. Divide the adjusted prices P prime by the length to get the normalized prices P double prime. To normalize A prime, you square all of the adjusted areas, add those squares, and take the square root of the sum. That gives you the length of A prime. Divide all of the adjusted areas A prime by the length to get the normalized areas A double prime. To recap, 1. Center the prices and areas by subtracting the mean. Then 2. Normalize the prices and areas by dividing by the length. The result is a standardized list of prices and a standardized list of areas where the sum of the terms in each list is 0, and the sum of the squares of the terms in each list is 1. Now we are all set up for the formula. Multiply each term in the normalized list of prices by the corresponding term in the normalized list of areas. So P double prime I times A double prime I. Add up those products. That's the correlation coefficient. In linear algebra, this is called the inner product or dot product of the normalized price vector and the normalized area vector. Let's give this a reality check. Imagine we are testing the correlation between Celsius temperature and Fahrenheit temperature. We know these are related by the linear formula F equals 1.8 C plus 32, so the correlation coefficient ought to be 1. Suppose we measure the temperature at 11 a.m., 3 p.m., 7 p.m. and 11 p.m. and find that the Celsius temperatures are 14, 24, 6, 0, and the Fahrenheit temperatures are 57.2, 75.2, 42.8, 32. The mean Celsius temperature is 14 plus 24 plus 6 plus 0 over 4, which equals 11. So the adjusted Celsius temperatures, C prime, are 3, 13, minus 5, minus 11, and the corresponding adjusted Fahrenheit temperatures, F prime, are 5.4, 23.4, minus 9, minus 19.8. The length of the Celsius C prime vector is 18. Divide C prime by 18 to get C double prime, the normalized Celsius temperatures. 3 over 18, 13 over 18, minus 5 over 18, minus 11 over 18. The length of the adjusted Fahrenheit vector F prime is 32.4, and the normalized Fahrenheit vector F double prime is 3 over 18, 13 over 18, minus 5 over 18, minus 11 over 18. We multiply C double prime by F double prime, element by element, and add the four products to get the correlation coefficient. This sum is brackets 3 over 18 squared plus brackets 13 over 18 squared plus brackets minus 5 over 18 squared plus brackets minus 11 over 18 squared. It all adds up to 1. This supports the claim that the procedure described previously, centering by subtracting the mean, normalizing by dividing by the length, and then multiplying term by term and summing, does indeed produce a valid correlation coefficient. To recap, you test for linearity by calculating the correlation coefficient. This section has shown you how to calculate the correlation coefficient. The calculation yields a number between -1 and +1. Here is a chart for interpreting the correlation coefficient.